office hour stream. Let me pull up Twitch now that we've gone live. Come on. Takes it a while to propagate. Okay, here we go. Awesome. All right. Why is the chat? Twitch iPad app could be better. Anything could be better. All right. Awesome. All right. Welcome to Office Hours. Who's got questions? I guess is the question of the day. Okay. It'll overwrite 1 byte of the password with a null byte. And then you'll still have the null byte problem. Okay, let's take a quick look. Let me familiarize myself with level 8. Okay. So all right, so can you tell me how you solved level 7? Let's start with that. Or think about how you solved level 7, right? Mm-hmm. Exactly. So for level 6, what you're doing is overriding the next pointer, right? To read out using puts the secret, right? All right, so let's actually start with a walkthrough of level 6, and then we'll go from there onwards. It looks like my slides are the wrong thing every time. Okay, hold on. All right. And of course, doesn't have, one sec, let me fix OBS. Okay, and my terminal. Oh, okay, at least that worked. All right, cool. So let's bring up level 6. Let's make sure that it's live. Okay, I'm logged in. All right, let's bring up 6 testing. Run. Oh, oops. Sure, run in practice. Let's download it. Let's inspect it. All right, jumping here. All right, here we go. So we can use malloc free puts, etc., etc. What are some additional restrictions in level 6? Let's take a quick look at Binary Ninja. Here we go. It looks like puts is only... No, so, hold on. There's a send flag command, which... So it's right here. All right. It makes sure that this local variable var98 is equal to this guy. So let's look at what happens with var98. var98 basically is a constantly being passed to scanf. Okay, cool. So right. All right, so it gets read in here. So this is our basically user input buffer. Cool. All right, this is obviously some secret. All right, here's the secret is at 429D4C on my binary, probably different on yours. And as you can see, this isn't position independent. Those are not position independent looking addresses. All right, so, and if we get this string comp correct, 8 bytes of it, then we have the password just sent out to us. Cool. How do we, so we have to leak out the secret. The secret isn't referenced anywhere else in main. It's just referenced here. This doesn't work with a decompilation. But anyways, it's just basically referenced in the setup of the stern comp. And over here where it's initialized to some random data, right? And that random data is seeded based on this flag seed, which is one of the constructors. And we can, break here and convince us of this in GDB. But that's basically, the point is we need to leak out the secret data. All right. So what else do we have? We have a malloc, where no. This is, where's our malloc? Hold on, okay. So this is our send flag. This is our scanf. Awesome. So we have a scanf where we can give it a page index, and it gets the pointer, the address of yeah, and it scanfs index as printf. Okay, I see, got it. So it lets us override an allocation. All right. And it lets us override that with a string. So basically any non-new line characters. And our dx9 is a pointer to an allocation that we chose with this index of RAX 39. So this is our chosen index. And this is our allocation pointer. And it basically says scanf with this format string, which is basically percent and then the size of the allocation and then s. So this is allows us to overwrite an allocation. Of course, it doesn't check if it is free or not. That's a big hint. Then we have, what is this guy? So this one is puts. It's our standard puts. All it does is just print it out. So it asks us what index we print out. Then it of course converts that to the actual index and then just puts it out. Right. And this is our, let's say, allocations array. Awesome. And we know the maximum size is 16, so it's just, I'm gonna try this, but Binary Ninja doesn't actually do this very well. Boom. Did that work? No, it's still okay. Cool. So that's this guy. All right. What is this? If we scroll up before puts, it's free. So this is pretty easy, self-explanatory. Why isn't it letting me make a... Okay, we no longer get to make... Let's refresh it. There we go. Free. All right. We just free the correct page. And then here, what do we have? The last one, if you scroll up, it looks like it's malloc, and it makes sense. It calls malloc, and it's also very straightforward. Just asks us for size, calls malloc. All right, that's what we have. So obviously using malloc, free, and scanf, and puts, we need to leak the secret and cause this program to give us our flag. Cool. So let's take a look at how to do that. Oops. All right. We know how to influence, poison the Tcache cache, right? If we start a script here, all right, and we send malloc, and it's going to ask us what page, and it'll ask us what size, right? Well, let me look at the malloc. Yep, it'll ask us what size. So in malloc, page allocation index and size, let's just do 16, and then it'll ask us the same thing. Or sorry, we allocate 2 pages, and let's just see what happens there. Okay, yeah. Unrecognized choice. we need to let's just malloc index 0 size 16, right? Why isn't it? Where's the prompt? Okay, let's do this. Is it buffering the prompt because I'm on a terminal? Okay, what's wrong with that? No, I'm happy with that, but this prompt isn't showing up. Hold on. I think libc is giving me. Okay, let's do this. What if I do? See, it's what the hell? Is it a pty? This is insane. Yeah. So we forgot to turn off buffering. But I needed to give me the data, but okay, that's fine. All right. Yeah, that's fine. That's fine. Yeah, so let's do this. Let's so I do my malloc. I do my second malloc. Yeah. That's bullshit. All right, and then let's do the quit. That's a good suggestion on Twitch. And then when we read, great suggestion. Boom, here we go. And it prints all of this stuff out. Okay, that's our bad. Sorry about that. We should have disabled buffering. Connor, can you open an issue? Oh, Connor, you went over 6 in your office hours? Okay. Got it. So we're gonna go over 6 a little more in depth. Okay. So basically, we allocated 2 things, and that's it. Of course, there's a testing challenge. It doesn't give you the output of where it was allocated, but what happens is the following, right? So we are actually not at this step. Imagine only A and B exists. We're at this step. We allocated A, and we allocated B. We have an urgent question on Twitch. No Frappuccino. It's not a Frappuccino. It's a Frappe. The Frappe is a very, very different beast. But no Frappe today. Unfortunately, I didn't have time to make it. It's a crazy kind of week. All right. So we have these 2 things. Now let's free them. Right? So we're going to send free, and we're going to send 0, and then we're going to do that again for 1. All right? Oops. I did it for 0 2 times. Of course, it caught the double free. and boom. All right, so we freed both of them. So now we are at the following situation. Boom. We freed B, or B was 0. Actually, let's do it the opposite. Let's free 1 first and then 0. Awesome. So here we freed 1, and then we freed 0. So there's now a doubly linked list in this Tcache entry. Sorry, a single linked list where the entry points to this Tcache entry 0 in our case, and then that entry points onwards to entry 1. All right. What does this mean? This means that if we do a puts of 1, actually, if we do a puts of 1, which was freed first, that should return nothing. All right, let's do this. Let's before this we do clean, and then we read until data colon, and then data equals p.readline. This should be just there should be a null pointer, and puts should give us yes, puts should give us nothing. And here it is. Boom. Okay. So if you do put 0, that is a pointer. Right? 0, 1, 1, 4, 8, 6, 0E. If you do it twice, did we get unlucky with addresses? You can see it's changing, but the last, this E0, and then the last nibble of the 6, so this is ASCII 6, that's hex 36. This last nibble is stable, right? So that's an index into the heap. Sorry, an index. This is a pointer in the heap specifically to where B is, right? So the awesome thing is that we can control exactly. We can override this value now, right? I should have really been doing a testing challenge of this. Let's switch to testing so we can demonstrate what's going on easier. Sorry, to teaching. Did I just get... I got booted out partway through. Hold on. I'm downloading a teaching challenge. Okay. Started the teaching challenge. Let's SCP it over. Okay. This will let us be more reasonable. We can actually see what's being allocated, but you'll see that we aren't dependent on what was allocated where. Okay. Here we go. All right, and let's actually convert all these to strings, except for this guy. What? How did that not get installed? Okay. Okay, I just installed a module that when you import it will give you a awesome .stir function for all bytes, so you can easily convert them to a string, so it can be printed out easier. All right, so here we go. Allocation 1 is at this address, 1C266C0. Allocation, or the 0th allocation is here. The first allocation is there. Then we free the first allocation, then we free the 0th allocation. So then when we print out the 0th allocation, it will have the address of the first allocation. You can see that address right here. 01, C2, 0F, sorry, 3F, goddamn, 01, C2, yeah. Why is this 301 C2 66? Oh, lowercase f. Yeah. So that's lowercase f. Lowercase f is 66. And then E0. Cool. Tcache works. All right. So that is, of course, what we're seeing is the Tcache linked list, specifically this entry, this pointer right here, pointing to the first, the previously freed allocation. All right, let's take a look at where we go next. One thing that we can do that is very exciting is overwrite this pointer, right? We have puts. We can do the same, but with scanf. So we overwrite allocation 0. And we can overwrite it with basically any address we want, right? So let's, for example, override it with 41414141, and then see what happens when we malloc that into 2. So someone asked on Twitch, does the size matter? The size matters right now. We wanted to use the same Tcache bin. So this size just needs to be consistent with this size and this size. All of this needs to be in the same Tcache bin. But the actual size doesn't matter as long as it's in Tcache. All right. Let's print out the return code. All right. So read everything out. Okay. So let's see what happened. We have our allocation 1 that was freed last. 5456E0. We have an allocation 2, 5456C0. No. Sorry. Allocation 0 was freed last. Yes. And so we got that back. What happens if we malloc again? Seg fault. Right. Why do we have a seg fault? Well, let's attach with GDB and find out. Where's my debugger? Oh, I need to be in screen for this. Okay. All right. Hit continue. Seg fault in Tcache get, where we are reading. So let's see what R8 is. This looks printable. Why is it printable? 1 4 1 4 1. Oh, lol. All right. Basically, it was this. What I meant to do was overwrite it. A B B B B. Right. 4 1 4 1 4 1 4 1 4 2 4 2 4 2 4 2. Because it just scanfs it. All right. You hit continue. All right. That's where we segfault. Why did we segfault there? We segfault there because when we let's go to here. So what did we just do? We overwrote this, right? And what happens when you allocate? When you allocate off of this structure, off of this configuration of the cache, you will return A, and then you will follow this link, follow this reference, and you will take this address, or the value of this pointer, and write it in here, right, to do this. But when we then allocate again, after having overwritten, so this address was 414141 42424242. We now put that in here in this entry, and the next time we try to allocate, it is trying to follow that to figure out the next address in Tcache to put here after its return. So dereferences are overridden 41414141, and we crash. Okay, so we need an address basically that will be returned as the allocation that is proper memory, right? All right. So let's take a look at what that address might be. And that address is, of course, the location of our secret. So let's take a look at main. Unfortunately, we were doing testing before, so none of our comments survived. Does this look reasonable in this? Not super reasonable. Okay. So anyways, here is the secret that we need to leak out. It is at this address. And at this address, we basically compare 8 bytes. And we need to, if we leak out these 8 bytes, we're home free. So let's log out of these GDBs. All right. So of course, what do we want to put here? We want to put here the address of our secret. Boom. So what's going to happen? We just overwrote the this value right here, with the address of where the secret data is stored in the binary. The binary is not position independent. We know that address, right? When we malloc next, malloc is going to return this the address of Tcache entry A, in our case Tcache entry allocation 0, and then it'll take this address and write it here as the new head of the bin, of that Tcache bin. The next time we do a malloc, it's going to return that address. It will allocate our oops, no, come back. I killed it. Sorry. it'll allocate it'll return an allocation that overlaps the BSS where our secret is stored. So now let's put this pwn p64 0x that. Awesome. All right. Oops. Continue. It exited normally. And here, our allocation, when we mallocked, it returned the address that we injected into the Tcache. How cool is that? So what can we do with it? Well, of course, we can put this out. All right. So let's do that. By the way scanf works, it'll when it's getting commands from you, it'll just read to the next white space, so you can perfectly fine do this instead of sending them all in their own line. And here's what we got. We did puts out of allocation 3. This is the data. So now, by the way, if you like to be cool, you can do p.interactive. Now we're interacting with this program. Send flag. Oh, it doesn't. Boom, and it works. Here's our flag. All right. Anyways, p.interactive was, because of the buffering, kind of not as fun. Okay, so we do this. Read until data : Okay, so this is our password. Send underscore flag. What's going on? Okay, password is correct. Okay. I was sending it probably represented as bytes with a quote around it and all of this stuff. Awesome. All right. Cool. Awesome. Okay, so that is level 6, right? So in summary, what we're doing is allocating 2 things. So there'll be 2 allocations in that will, once we free them, go into one Tcache bin. Each Tcache bin is a singly linked list. This last thing we freed will have a pointer to the first thing we freed, or whatever, the thing we freed before it. So allocation 0 will have a pointer to allocation 1. We can print that out just to, assure ourselves this is completely unnecessary to the actual exploit. We override it with a pointer to the value that we want to read out using puts much later. Then we allocate once, we get a reference to our old allocation 0. When we allocate again, we get a reference to the address that we injected into the Tcache. And then we can just write it out, and that is our address. All right. So then, of course, 7 is basically this iterated twice. That's very straightforward. What about 8? So now we get to the original question. How do we handle the white space armoring in 8? So let's take a look. All right. I'm going to go to level 8. Launch it up. All right. Level 8 has the same secret thing, right? The same scanf functionality, the same puts functionality, the same free, and the same malloc. All right. The difference is the way that it initializes the secret is different. It's white space armored. So let's SCP it over. No. All right. So the address uses white space armoring, right? And says, okay, you know, notice that there's a new line in the address. Why is this a problem? Well, this is a problem because if we go back and try to do our original technique here, but just use this address instead, right? Let's just, oh, you didn't see any of this. This is what it says when it runs. It says the secret is stored at 426E0A, and it uses white space armoring. That is this new line in the address. Okay? You can actually confirm that when you're not on a teaching level. Here, where it does this string compare, 462E0A. Okay, so what do? We just change the address here, try to run the same attack, and there's an EOF error. And the EOF error is after this puts 3. Why is there an EOF error after this puts 3? If we do, of course, the answer to most of your questions is going to be check it in GDB. Boom. All right. My mind just went blank. I apologize. Okay. Hit continue here. Boom. Sec fault. And it's at our old friend, the instruction that pulls out the next variable, the next pointer to update our Tcache. The head of our Tcache list. And it's trying to get 426E. The 0A got chopped off because scanf chopped it off. So we are in a little bit of trouble here. All right. So you have a number of ways forward, right? You have a number of ways forward. One way forward is saying, okay, no problem. I just won't get the first byte. Right? Instead of this 0A, let's do 0B. We still crash on the puts 3. Why? Because 0B is a vertical tab. It's still white space, and I think scanf will still break on it, right? Let's confirm this by Okay, we're attaching. Continue. Yep, same sort of thing. It didn't read the last nibble. We can do 0C. Same sort of thing. Oops. Still didn't read it. 0D, also a same thing. 0D is also a new line. 0E. Okay, this one seems to be not crashing. Why isn't it? Why is it hanging? It didn't quit after the quit. That's weird. So, tricky, right? Because that's a lot of characters that we need to brute force. If we're going to... and then it prints it out and... no, that's weird. All right. So there's something I'm not clear about. Hold on. Why did this... What got screwed up? Why isn't it terminating here? And why did nothing get printed? I forgot to change this to level 8. There we go. There's probably nothing at that location, of course, in level 6. All right. So we got a password, but this is the several bytes into our password. So then we'd have to brute force a bunch of bytes. That is no fun. So now let's think about how we would solve this otherwise. Right? How would we solve this otherwise? I'm having a brain dump right now. Oh. All right. What is the secret? So this is a valid thing. You could read out the password from here. If we make this a little bigger, probably we can get more of it. Okay, so this is the password for, starting from 0E. this RJXSZQW or ZJWQ. That's 8 characters of it. Of course, we could go starting from F. That's 1 more character and so on, right? You can get it 8 characters, 8 bytes at a time over multiple executions or multiple iterations of this thing. You can go, here's another one, J, and so forth, right? So you can leak out everything but the first bunch of characters. And then you could brute force those, right? So on Twitch, someone got the intended solution, right? And they said, listen, what you really need is this. You need this string comp to pass, right? The program has no built-in way, intentionally, of changing these bytes. But that doesn't mean that you can't do it, right? What do you care about what data is actually here? You just want it to be correct. So when we get this overlapping allocation, we want to overwrite it starting from 0A, but we can't because 0A is hardened, ASCII hardened, right? It's a new line. Scanf will stop reading at that 0A. So just say 0, 0. Scanf is perfectly happy with that. And we'll receive an allocation, right? What does it? Oh, why won't it quit at that? Okay, anyways, it'll receive this allocation. Oh, I see what's going on. Okay. And then it'll return that address perfectly happily. Won't crash. All is good. So now we have an address that is 10 bytes away from our secret. Our 16 is 16 bytes. When we do a scanf, scanf will allow us to override the entire allocation. And it thinks that that allocation is 32 bytes long, right? So now, if we do scanf3, it'll interesting. So this is all right. So this is the usable space that it receives, right? When it reads the metadata of this chunk. So it'll read at this allocation -8, or that address, and then the 8 bytes before that address is the usable space. Those bytes are obviously null. %0s looks like bad news, but it'll actually, if you go man, there's a, if you do man scanf, there is a, where the size, %0f is special. Connor, did we find where this is documented? All right, so let's just Google for it. All right, scanf with a specifier of 0 basically means it's not valid C, but it... All right, the bottom line is it'll let us write whatever we want to write, right? So if we do this, we have this scanf. If we send a bunch of A's, okay, this is now perfectly happy. We can now, to show you that we overrode this allocation, of course, I can do a puts 3. Here's a bunch of A's from that data. And now we can do send flag. And then a bunch of A's. And it'll compare the first 16 bytes of this against the first 16 bytes of this. And it'll happily succeed. Cool. So that's 2 different ways. I didn't do the brute force, but we could do the brute force, of course. There's a third way of pulling this off, and that is fixing up this chunk so that you don't have to rely on this scanf of 0, right? Here's how we do this. We allocate hold on. Okay, so the size that the scanf command of the challenge, right? It's the scanf command of the challenge. It calculates the size by calling this malloc usable space. Malloc usable space just looks at the 8 bytes beforehand, subtracts OX10 for the chunk, adds 8 for the prev size field of the next chunk's metadata. So it basically just subtracts 8 from the 8 bytes before the chunk, and then it returns that to you, right? So how can we set up? Actually, I'm going a little off script. I'm pretty sure that we can set up this chunk with the right size, so we don't have to rely on this scanf of 0 bug, or not bug, but corner case. Man, I need more sleep for this heap stuff. Okay, if we allocate okay. So we have allocated this guy, and right now the 8 bytes before this, so at EF8 is a null byte. So we need that byte to be non-zero. So what we actually need to allocate 2 more helper guys in the beginning. This is the advanced solution. It's more elegant. If we allocate 2 more helper guys, 10 and 11, so that we can kind of just forget about what we just screwed up in the T cache, because right now the next allocation is going to be whatever this was, it'll be null bytes. Oh, actually, so that'll be fine. So that's fine. Tcache is not broken. Okay, cool. So let's malloc 3 is our the allocation pointing to secret. Okay. Let's do malloc 4 32, malloc 5 32. We'll set that up. Actually, let's do malloc 6 32. So these are 3 normal heap allocations. And actually, let's make sure okay, perfect. That didn't die. So we have our heap allocations. Then we have our injected Tcache guy that's right before that secret. And then we have 1, 2, 3 normal allocations. Everything's going according to plan. What do we do now? We free 6. And then we free 5. So now 5 is pointing to 6. I can prove it to you by doing this same thing here. Puts 5. There it is. So 5 was... 5 was BE0750 and 6 was BE0780, and this guy is pointing to 780. Now we write 8 bytes earlier here. This is insane. So this is F8. We inject this address into the Tcache. Then we malloc twice. Okay. We fucked up somewhere. Ah, I forgot the scanf. Scanf into 5. All right, so we injected this. We managed to allocate an allocation 8 bytes before our allocation where we're at right now. So that allocation's next pointer is going to overlap with our original secret allocations, this guy's size. Then we're going to free our normal allocation, and then we're going to free our overlapped allocation. And this guy failed. Why did it fail? Ah, it failed because our metadata is incorrect. Now we have a chicken and egg problem. So the scanf0 bug is the only way to solve this, huh? Or the scanf0 corner case. Or the brute force. All right, never mind. We went on a tangent. Sometimes it doesn't pay off. All right, so that is 8. What were the additional questions? Could you not just scanf like printf the canary? Lambda, what do you mean by that? Lambda. So scanf is a little different. Scanf reads until the next new line or space, white space character, not until the null byte. That is what I was doing. Yeah. So Connor, the problem with doing that is when, in order to write the next pointer there, you have to free it, right? When you free it, it looks at the size. It sees the size is 0, and it says this is not a valid chunk, and then it kills the program. I see what you're saying, Lambda. So, on Twitch, we have a suggestion to allocate here. Of course, the secret is at 0A. We allocate here, and then we scanf into it 10 bytes or whatever to just write A. The problem is scanf will write a null byte. And so we won't be able, and puts will stop printing at that null byte. But yeah, so the solution is just override that whole password. Cool. Another question, would this approach work for 6 and 7? Yes. It overcomplicates things a bit, but this approach would also work for 6 and 7. Mm-hmm. Yeah, 9, you can't allocate anything into this, or on 9, you the program will discard. Let's open up 9 real quick, rather than try to describe it in a clever way. We'll just take a look. Actually, let's open up testing so that we have to reverse fewer things. Okay, here we go. On 9, there's an additional security check added, additional added, that does this. So it does a malloc, and then it says, okay, this, by the way, this is the index, the allocation, the result. So here we write to it. That's this is our allocations array. This is our allocation index. And this is Binary Ninja being crazy. So it basically says if, this is a crazy way of putting it, but basically if these allocations are, if the allocation is in a location greater than global, which is this page right there, or this address right there, and less than some other address, assert fail, which is, I think this is a binary. Let's look at this in the low level, or the assembly. There we go. Oh, that's the wrong one. My God. There we go. Invalid allocation detected. So it looks at this global label, and then it adds 10,000 to it. So if it's from this address, 42000, all the way to, oh my God, all the way to 43000, it will tell you invalid allocation detected, and then it'll put a null byte in the allocations array. Think about what that does. What is the state of the program like before the malloc and after this error? That is what you're assuming is not what's going on. You're assuming that that allocation is undone. There's nothing here that undoes the allocation. The allocation still happens. Think about the implications of that, even if you don't have the pointer to it. Which part? Oh, sure. So here, this right here, if the check fails, if you are allocating something that is between this address, and of course, the password is between this address and hex 10,000 away from that address, right? If you allocate something that goes into there, it'll tell you invalid allocation detected, and instead of writing the pointer that you allocated, it'll write a null byte, or it'll just write null, right? So it'll set that that entry in the allocations array to 0. Now the allocations array is just internal to this program, right? Has nothing to do with libc, has nothing to do with the malloc state, has nothing to do with, you know, more or less anything. No. What happens is there's an allocations array in the program. This guy, right? And it'll, so when you malloc something in the program, when you say malloc, it'll do the malloc right here, and it'll move that end, blah blah blah, and it'll move in the end that the result, the pointer into this allocations, right? So it says allocations 3 equals blah, right? That's this line. Then it'll do this check and say, oh shit, that allocation was invalid. It ended up in the BSS. And then it'll overwrite that pointer it had just written. It won't touch the BSS at all. It'll overwrite the pointer just wrote with 0. It overwrites the local pointer on the stack to that allocation. Run through it in GDB and take a look at what this actual address evaluates to. All right. There was a question on Twitch. What is the plan for Wednesday? The current plan is we're going to have either on Wednesday or Thursday, we'll have the extended Q&A as normal, and we'll launch the challenges. It's a really crazy week, so we're doing our best. But Veterans Day, despite being known well and ahead of time, somehow snuck up on us unexpectedly. All right, so yeah, the key thing with level 9 and 10 is think about the true implication of what happens here. And think specifically about what doesn't happen here. All right. Thank you for joining us. As always, if you have questions, shoot us an email. Email is much better than Slack because then than Discord, because then we can track it. If you need to ask us specifically, otherwise the help channel and the collaboration channels, our Discord, are open. If you got 9 but not 10 using this logic, as someone in Twitch is saying, then you used the wrong, well, not the wrong logic because you got it, but you used the wrong logic for 10. The hint is in 9, this check is imperfect, right? This check, you can kind of bypass it more or less. In 10, you cannot. It is a correct check. Just take a look at 10. Let's take a look at 10 right now. 10 testing, inspect. So in 10, hold on, no, this was easier like this, right? Hold on, let's do this. Let's open up malloc. There we go. Here's our call to malloc. Then in 10, we... God damn it. Why is this broken suddenly? Okay, I can't, for some reason, scroll the graph anymore. Okay, anyways. In 10, we do the malloc. As a reminder, in 9, we check if the address is greater than the address of global and less than the address of global plus 10,000, we allow the allocation. In 10, it's a little different. We check the address of global plus 10,000, and if it's less than that address, we disallow the allocation. So there's no more lower bound. It's just any address less than global plus hex 10,000 bytes is disallowed. So this check is different, right? It catches more. This is the only difference between 9 and 10. If you can solve 10, you can also solve 9. But obviously solving 9 is much easier given that difference in check. Think about it. All right. Awesome stuff. someone asked if there's a reason that only 8 bytes are printed. And that is a great... And I think that was back on level 6, right? Let's take a quick look. Back to level 6. So in level 6, fuck. Let's disable this. No, sorry, level 8, level 8. Okay, level 8, 8 bytes are printed. Why 8 bytes are printed is an excellent... Oh! Yeah. 8 bytes are printed. I'll explain to you why. Let me... Where are my slides? Recall what happens here. We have our Tcache setup, right? Next is a pointer to B, and the key is a pointer back to our Tcache per thread struct. What happens when we allocate is, for whatever reason, that pointer to the Tcache per thread struct is nulled out. So everything after 8 bytes is null. So when you print, you only get 8 bytes. You'll have to relaunch and get the rest later. And if you don't want to relaunch, you can read it from the end in using successive allocations. First the last 8 bytes, then the previous ones up until the white space armoring takes effect. All right. Thank you for joining. Sorry if we went on a couple of tangents. That's where we learn. We'll see you on probably Wednesday, either Wednesday or Thursday or both, for the race conditions module. We're pretty excited. Goodbye and good luck.